can start talking about paramagnetism, and we want to basically go over a few things that characterizes a paramagnetic material. First of all, this is going to occur in materials that have net magnetic moments. So net magnetic moment is required. However, these magnetic moments are weakly coupled, so the forces that they exert on each other is not very strong, so we have weakly coupled magnetic moments. And when the applied field is zero, as you can see in this figure, these net magnetic moments are randomly oriented. And what causes this random orientation? It's basically the thermal energy. So with no external field, thermal energy, kT, Boltzmann constant times temperature, causes random alignment. So the moments are randomly oriented. When we apply a magnetic field, as you can see here, they'll have a net component in the direction of the magnetic field, so they will become somewhat ordered. So which materials fall into this category? Transition metal salts. For example, iron chloride. So what happens in these transition metal salts is that, for example, in iron chloride, the transition metal moments, iron moments, are separated, so they have weak coupling between them. On the other hand, rare earth salts rare earth metal salts, these have localized F electrons without any overlap, and so there's weak coupling between the moments of these electrons. Elemental examples, paramagnetic metals, we have aluminum, a good example. Paramagnetic gases, we have oxygen, a good example. And furthermore, we know that all ferromagnets become paramagnetic above the Curie temperature. For T temperature greater than Tc, Curie temperature, the ferromagnets go through a phase transition. All ferromagnets become paramagnetic. So they go through a phase transition. The susceptibility for paramagnetism is m over h, that is positive. It is small, 10 to minus 5, 10 to minus 3 range. And if you look at the corresponding value of permeability, now I write this in SI, B is equal to mu 0 m plus h. So if I divide this by h, I can write this as mu is equal to mu 0 1 plus chi. So mu divided by mu 0, the relative permeability is 1 plus chi. Since chi is slightly greater than 0, the relative permeability is slightly greater than 1 in this case. The susceptibility has a temperature dependence. It's 1 over T according to Curie law. This is basically due to having localized weakly interacting moments. And however, there is a class of materials called Pauli paramagnets where the susceptibility is not temperature dependent. So this is, need to watch out for this in Pauli paramagnets. Okay, so basically these are some of the things we should be aware of about paramagnetism. The material has to have a net magnetic moment. Those moments should be localized and weakly coupled. With no external field, the thermal energy kT causes random alignment of these moments, but when a magnetic field is turned on, there is a net alignment in the direction of the magnetic field. Transition metal salts like iron chloride and rare earth metal salts, where we have localized moments, we can have paramagnetism. Paramagnetic metals, example is aluminum, gases, example is oxygen. For temperatures above the Curie temperature, all ferromagnets become paramagnetic. The paramagnetic susceptibility is slightly greater than 0, it is small, and the corresponding relative permeability is slightly greater than 1. It has a characteristic temperature dependence. Susceptibility varies as 1 over T according to Curie law, which we will derive. And on the other hand, if we're talking about Pauli paramagnets, in another class of paramagnets, we're going to see that in that case, the susceptibility is temperature independent.